Yes, hi everyone.
Hi.
Let me share my screen. Okay. So, yes, can you see my screen?
Yes, that's all fine.
Okay. So yes, hi. My name is Constantinos. I'm currently working in Smart Internet Lab, but I'm also towards the end of my PhD in license exemption at millimeter wave spectrum sharing between mobile operators, which I started back in 2016 in CSN. So what is spectrum sharing? Instead of chopping up the spectrum and exclusively licensing it to operators, partly or fully sharing the spectrum allows operators to access a larger amount of resources at any given time or place. This enables a higher spectral efficiency, spectral usage. However, it also comes with a higher interference levels and lower spectral efficiency. The main question is whether spectrum sharing can make up for the loss in spectral efficiency in such a degree that the mobile networks and their users can benefit from. Starting with the spectrum under investigation, millimeter wave frequencies are considered one of the main enablers of spectrum sharing. Networks can take advantage of bandwidths in the order of gigahertz, and links of much wider bandwidth could benefit the connected users in terms of throughput, despite the reduction in the SINR. Meanwhile, the propagation characteristics at such high frequencies can be considered a natural interference mitigation mechanism. The high propagation losses limit the range of millimeter waves, which is the range is much smaller than the one of microwaves. This allows a very dense deployment, cell deployment with relatively low inter-cell and inter-operator interference. The small wavelengths involved in millimeter waves also enable the sustainable use of multi-element mobile and base station antennas. As a result, directional beamforming with narrow beam widths can be employed, providing high resolution spatial multiplexing with low probability of interference. So in the last few years, I've been investigating how spectrum sharing cellular networks can compare to conventional exclusive license networks. An advanced ray tracing engine was used to simulate the high density network with multiple operators. And we studied the spectrum sharing in different network deployments, such as spectrum sharing with sectorization or non-orthogonal multiple access strategies. At the moment, I'm currently investigating ways of improving the network performance in such spectrum aggressive implementations by optimizing the allocation of the millimeter wave resources. The network simulation engine that I'm using has three main components: the antenna model, the channel model, and the network model. Measurements from a single patch antenna were used to generate a multi-element antenna arrays, as the one shown in the figure on the left. So by placing multiple antenna elements half a wavelength apart, different user and base station antennas were deployed within the, let's say, simulation environment. And to make our model more realistic, the beamforming capability of all antennas was limited by introducing beamforming errors or by using a codebook, which limited the radio to, let's say, a predefined set of directions. To to a predefined set of directions in the azimuth and elevation planes. A ray tracing tool was used for channel modeling. A map database which 3D captured all aspects of a real location was used to simulate the propagation of millimeter waves in a real environment. This included roads, buildings, and trees, and their corresponding material properties, which were taken which we have based on measurements we took in the area for in previous studies. As you can see in the figure in the center, the two figures, a map environment was used that covers the area of half a square kilometer, give or take, in central Bristol around the University of Bristol campus area. Different network models were used to investigate the different network strategies. And given the, let's say, the high processing time, because this is such a complex model, a full network simulation includes only a single downlink only capture of the network. Some of the main results. So some of the main results that we have from previous studies. You can see spectrum sharing in different network strategies. So firstly, we only have spectrum sharing, and we compared it with the exclusive license model, 26 and 70 gigahertz. And you can see the gray bars correspond to the exclusive license throughput performance, while the say the maroon ones, the reddish ones, correspond to the spectrum sharing throughput performance. In the figures in the middle, which is spectrum sharing with sectorization, you can see the SINR, signal to interference and noise ratio performance of different exclusive license spectrum sharing approaches, implementations, as well as the throughput on the bottom row. And in the last set of figures on the right, you can see spectrum sharing along with a beamforming based non-orthogonal multiple axis approach. And what you can see in all of the results is that spectrum sharing is very, very beneficial compared to the conventional spectrum axis methods, even though the lack of improvement in the 5th percentile users, which corresponds to users with low signal, low signal reception, means that interference mitigation algorithms should they should be employed in order for the lower SINR users to benefit from spectrum sharing. Yes, that was my presentation. Thank you all for joining, and please feel free to ask any questions you may have.
Okay, thank you, Constantine, for this very, very interesting talk. Can I ask a question? All the results that you have demonstrated are products of simulation, correct?
Yes.
Have you validated, or do you have any plans to validate your results versus experimental data?
So the main difference between this type of study and previous spectrum sharing studies is the high density of the users and base stations in the simulation, as well the high level of, let's say, realism, how realistic the engine is using ray tracing and the antenna model based on measurements. So yes, in the future there is, let's say, a motivation, that is the target to compare this with previous studies. But currently I can't find any studies that have this high amount of users and base stations in their simulations. On the other hand, it's really difficult to test this on a practical network because of the lack of millimeter wave support and technologies. So we'll see in the future.
But maybe feeding realistic emission patterns of the antennas into your simulation for the physical should be relatively easy. I also have another question. So, could, obviously, spectrum sharing is beneficial, as you mentioned. Can you quantify these benefits? I mean, sort of a summarize, but in a quantifiable way, the results that you demonstrated.
Yeah, so yeah, okay. So if I'm gonna say the percentage gain between, let's say, the exclusive license model and spectrum sharing, what we found was, on average, it was at least, let's say, 100% gain, which could go up to, I don't know, 400%, maybe 500%. But yeah, what's interesting is basically it's a resource utilization. So the resource utilization might be like more than 800% more resource utilization in spectrum sharing compared to exclusive license model. So with the right, let's say, interference mitigation mechanisms, we might be able to get more performance out of it.
Great. Very, very interesting results. Thank you very much for your presentation.